Okay, this one here we have an inclined plane problem. We know how high the hill and how long the ramp is, and we know the speed they reach at the bottom. We want to find the coefficient of friction. So let's draw a force diagram first to get our creative juices going here. So inclined plane, we always rotate that axis, right? All right, had to make that sound in the video once. We rotate the axis. Gravity is still straight down. And we rotate the axis so that the normal force is on an axis and the force of friction is along an axis. All right, so I'm just trying to differentiate these arrows a little bit from the axis they're on. All right. So this is theta. We don't know theta, but we can get it from the geometry here, right? The sine of theta, right? Sine of theta is equal to 15 meters over 50 meters. So, opposite over hypotenuse. So the sine inverse of both sides, we take 15 over 50. Sine inverse of 15 over 50 is 17.5 degrees, 17.45. So I'm just going to say theta is equal to 17 degrees. Great. Now we get to work on our diagram right here. So the object's accelerating down the ramp, right? So the acceleration's this way. I usually like to leave room there. Acceleration's down the ramp, so make this the positive direction. Make that the positive y. So sum of the forces in the x direction equals mass times acceleration in the x direction. I'm going to do this one a little bit differently. I'm going to do the x direction, then do the y direction. So in the x direction, we're going to have the force of gravity, okay, it's x component. Fgx is in the x direction. Fgy is in the y direction. X and y component of gravity. Now I don't make these solid arrows because they're components, right? Fgx is the length this side of the triangle. So it's going to be Fg, which is 200 newtons, times the sine of 17. So 200 newtons times the sine of 17 degrees. That's what's pulling down the ramp. Pulling up the ramp is the coefficient of friction. That's the negative direction. So it's negative mu times Fn equals the 20 kilograms times the acceleration. Now the acceleration, we also have to do a little side calculation for. Acceleration equals, well, change in velocity over time. Oh, wait a minute, I don't have that. So we've got to use a kinematics formula to get the acceleration to then use over here. All right, so to get the acceleration, we're going to use the v squared equation. All right, see below. So v final squared equals v initial squared plus 2a delta x, because we know delta x, we know v final, we know v initial is 0. So a is going to be equal to 7 squared divided by 2 times 50. So I just solved this for a. So vf squared, so 7 squared is 49 divided by 100. 2 times 50 is 100. So we've got 0.49 meters per second squared for our acceleration. All right. So, oh boy, bells are ringing. Everything's crazy. Sum of forces in the y direction is 0. Well, let's go back over here. The trick here is we know a now, so I could put that in. We solved that using kinematics. I don't know mu. That's what we're looking for. And I don't know Fn. Well, I can get Fn from over here. So, sum of the forces in the y direction. Fn is positive minus 200 newtons times the cos of 17 equals 0. That's negative. The y component of gravity is negative. So Fn equals 200. Bring this over here. It's going to turn out positive, right? So 200 newtons times the cos of 17. 200 cos of 17 is 190. So Fn is 190 newtons. So we can now solve for the coefficient of friction. We know that's 0.49. So that's going to be roughly 10. We'll bring that over here, this over here. Let's find 200 times the sine of 17 first. Let's go ahead and get that. That is 58. So this is 58 minus the coefficient times 190 equals 20 times 0.49. All right, I guess I'll show that. All right, so 58 minus mu times 190 equals 9.8. Bring this over here, this over here. So we get 58 minus 9.8 is 48.2 equals mu times 190. Divide both sides by 190. We get mu equal to about 0.25. All right, well, that's all we need there. So again, this one's kind of funny because we had to use geometry to get the angle of the incline, and we had to use kinematics to get the acceleration. And then we could use Newton's second law in each direction to then solve for the coefficient of friction. Next one here. All right, we've got kind of a funny one here. The tugboat through the canal, angle on each side of the chain is 15 degrees. Approximate mass of the smaller cruise ship is about 50 million kilograms, dead, blah, blah, blah. X-rays. All right, so top view, here's the cruise ship. Now, basically ends up looking like this. All right, this is your x-axis and y-axis. We're not worried about gravity and normal force. It's not a normal force, actually it would be a buoyant force. This is FT, FT. They're both the same. It's 15 degrees between them. So that means that's 7.5 degrees on each side. So this is just one-dimensional motion. We don't even need to worry about the y. We'll say that's the positive x, positive y. We're looking from the top down. So sum of the forces in the x direction equals mass times acceleration in the x direction. So we've got Ft times the, oh yeah, basically we've got the two x components here of this vector. So Ft times the cos of 7.5 plus Ft times the cos of 7.5 equals 50 times 10 to the 6 kilograms, 50 million kilograms, times the acceleration of 0.0010 meters per second squared. So add these two together. So cos of 7.5 is a pretty small number, or sorry, number pretty close to 1. 0.99, so 0.99 times 2 is 1.98. So this, each one of these is 0.99 times Ft. So this adds up to a total of 1.98 Ft equals 50 times 10 to the 6 times 0.0010. That's 50,000. Divide both sides by 1.98. 1.98. Force of tension of the rope must be about 25,000. newtons to 2 sig figs. So that one's a little bit easier. Kind of a weird setup, but not too bad. I'll record a couple more in a second here.